Welcome back. So we're discussing the Laplace transform of some basic signals. So continuing with that, let's take Laplace transform. Let's see what is Laplace transform of a DC signal. Fine. Let's first see DC signal. DC signal is which has a constant value. So we can say it's a signal of this type x of t having some constant value, say a naught. Now if I apply the conventional method, x of s is equivalent to minus infinity to plus infinity a naught e raised power minus st dt. A naught is constant, so we can take it outside. So internally we will have this thing. Fine. And it will be minus a naught by s e raised power minus st between the limits minus infinity and plus infinity. So that means it is minus a naught by s e raised power minus s infinity minus e raised power s infinity. As we proceed the limits, upper limit is infinity and lower limit is minus infinity. Now this thing here, it will converge. For this thing to converge, s should be positive, so then only it will be e raised power minus infinity, which will be 0. And for this thing, s should be less than 0, because then only it will be e raised power minus infinity, which is 0. Now this is a contradictory requirement for these two components. Fine. So for first exponential to converge, s should be greater than 0. For second exponential to converge, s should be less than 0. Therefore, since this is contradictory, we conclude because of this, and there is no overlap, greater than 0 and less than 0. So there is no overlap between the two ROCs. So the Laplace transform of what you call a DC signal which is defined for t is equal to minus infinity to plus infinity, it simply does not exist. Fine, because we cannot agree upon the ROC. There is no common ROC for the two components. Similarly, we have a signal, function, what we call the Signum function. It is defined as SGNT. It is the difference of two unit step functions, u of t minus u of minus t. Now we have earlier found the Laplace transform of the unit step function. So iska transform for this, sigma is greater than 0, and for this sigma must be less than 0 for their convergence. Again, it is a similar kind of a situation like we have in these when we try to find out the Laplace transform for DC value. So यहाँ पे भी exactly we can't have a common region of convergence for the two components, which again means that Laplace transform of Signum function does not exist because of the lack of convergence. We don't have any common values where these two functions will converge. Hence, we cannot define the Laplace transform. Okay. So next, we will try to find a Laplace transform of a ramp function. And ramp function is defined as r of t equivalent to t u of t. So let's try to find out. So Laplace transform, let's denote it by r of s. Since u of t साथ है तो we will have limits from 0 to infinity t into u of t e raised power minus st dt. Now if you try to solve this integral, yeah, you can say it will be slightly difficult to solve this integral because it involves multiplication of two functions t and e raised power minus st. So you'll have to use that uv rule. But we can use one of the properties of the Laplace transform. We had the property that if x of t, it has a Laplace transform of x of s with some region of convergence, say r, then actually it was minus t into x of t. It will be d by ds of x of s, that is differentiation in the s domain with the same region of convergence. आप नेगेटिव साइन को चेंज भी कर सकते हैं. So instead of putting the minus here, we can include it here. Right? So we'll be using this property here. So specifically what we'll be doing is we already have u of t. We know what its Laplace transform is. It is 1 by s with region of convergence sigma greater than 0. Then if I consider t into u of t, its Laplace transform will be minus d by ds of 1 by s. That is the derivative of this thing. So you can calculate this. It will be minus d by ds of s minus 1, and that will be 1 upon 1 into s raised power minus 2, which will be 1 upon s square. Okay? So Laplace transform of t into u of t, its Laplace transform is 1 upon s square with region of convergence being sigma greater than 0. Similarly, we can compute the Laplace transform of higher powers of t. For example, if I have to calculate t square u of t, its Laplace transform, then again I can use the property that t square u of t is equivalent to t into t ut. Now again I can use the same what you call property that we know what the Laplace transform of t into ut is. It is 1 upon s square with the region of convergence sigma greater than 0. So if I have to find t into this function, it will be minus d by ds of 1 by s square. And when you compute this derivative, it will be 2 divided by s raised power 3. Similarly, you can continue and we can come up with a generalization that Laplace transform of t raised power k u of t will be equivalent to k factorial divided by s k plus 1 as a general expression. Like here, if you use, here k has a value of 2, so if I put k value equivalent to 2, that will be t square u of t. It will be 2 factorial divided by s3, which is 2 upon s cube. Fine. Then next, let's try to find out the Laplace transform of a cosine signal. Cos omega naught t into u of t. So this is my x of t. So we know we can use the Euler's theorem that cos omega naught t is 1/2 of e raised power j omega naught t plus e raised power minus j omega naught t. Okay. So x of t is 1/2 of e raised power j omega naught t plus e raised power minus j omega naught t into u of t. So if I have to find x of s, it will be 1/2 बाहर निकालते हैं, integral 0 to infinity because of u of t, and internally it will be e raised power j omega naught t plus e raised power minus j omega naught t e raised power minus st d of t. Now again, instead of solving this integral, we can separate it into two. 1/2 0 to infinity e raised power j omega naught t e raised power minus st dt. Then the second one will be 1/2 0 to infinity e raised power minus j omega naught t e raised power minus st dt. So if you wish, you can just combine these two exponentials. So this will be e raised power j omega naught minus s into t d of t plus 1/2 e raised power minus j omega naught plus st dt. Then it will be 1/2 then this j omega naught minus s and e j omega naught minus s into t between the limits 0 and infinity. And this right here will be minus 1/2 j omega naught plus s, then e raised power minus j omega naught plus s t between the limits this. Now again, there is the same thing, that when we proceed this exponential factor to limits, it should be 0. Now यहाँ पे this thing, that is j omega naught minus s, should be less than 0. Then only it will become e raised power minus infinity as t proceeds to upper limit infinity, which means j omega naught should be less than s. Yeah, I can say s should be greater than j omega naught, but s is equal to sigma plus j omega. It should be greater than j omega naught. If we compare real and imaginary parts, it implies, because on the right hand side there is no real part, so sigma should be greater than 0. Right? Similarly, if you consider this thing, यहाँ पे we have to ensure j omega naught plus s should be greater than 0. It should be positive, which means s should be greater than minus j omega naught. Again, if we compare, s is equal to sigma plus j omega. So sigma, there is no real part on the right side, so we can say sigma is greater than 0, because on both sides, both exponentials, the real part is missing. Okay? So we have to ensure this sigma greater than 0, and when we ensure this, we are basically ensuring that this also converges, this also converges. Okay? So ये जो आएगा, it will be 1/2 j omega naught minus s, then it will be e raised power minus infinity minus e raised power 0, then minus 1/2 j omega naught plus s, then again e raised power minus infinity minus e raised power 0. So this will be, if I slightly rearrange it, just a second. Okay, so this will be my, so it will be 1 by 2 s minus j omega naught, this thing, and this right here will be plus 1 by 2, so s plus j omega naught, right? And for the entire sum, sigma should be greater than 0. So you can simplify it further. I think 1 by 2 बाहर निकालते हैं. It will be 1 by s minus j omega naught plus 1 by s plus j omega naught. If we factorize it, it will be 1 upon 2 s square minus omega naught square s plus j omega naught plus s minus j omega naught. So this and this will go, then s plus s is 2s, so it will be 1 by 2s divided by s square minus omega naught square, which will be s divided by s square minus omega naught square, right? So Laplace transform of cos of omega naught t u of t is equivalent to s divided by s square minus omega naught square, with the region of convergence being sigma greater than 0, right? Similarly, you can find the for a sine function. So if I have x of t as sine omega naught t u of t, again we know from the Euler's relation that sine omega naught t is equivalent to 1 by 2j e raised power j omega naught t minus e raised power minus j omega naught t. So you can solve it, so it will be x of s 0 to infinity 1 upon 2j e raised power j omega naught t into e raised power minus st dt. This will be first integral. Then 0 to infinity 1 upon 2j e raised power minus j omega naught t e raised power minus st d of t. So this thing will be equivalent to 1 by 2j 1 s minus j omega naught, and you have to ensure here again sigma greater than 0, following the same logic जैसे यहाँ पे हमने किया था. And this thing right here will be 1 by 2j 1 divided by s plus j omega naught. इसके लिए भी sigma is greater than 0. Then you can combine the two, and ultimately it will be equivalent to omega naught divided by s square plus omega naught square with region of convergence sigma greater than 0, right? So these were some basic signals and their Laplace transform. Stop here, and the next video we'll look at the system representation and system analysis through the Laplace transform.